Good morning, students. This is Murthy, sir. In the last class, we discussed about electronic theory of valence proposed by Louis and Kozel, and we learnt about ionic bond and covalent bond. We discussed some examples. Today, we will discuss about bond length and bond energy, drawbacks of electronic theory of valence, the salient features of VSEPR theory, its limitations. All these we are going to discuss today. Students, bond length or bond distance is the equilibrium distance between the nuclei of two atoms which form a covalent bond. Students, bond length or bond distance is generally measured in nanometers or angstrom units. Students, in this diagram, you can see the representation of bond length between two atoms. 1 nanometer is equal to 10 to the power minus 9 meters. In molecular geometry, bond length or bond distance is defined as the average distance between nuclei of two bonded atoms in a molecule. So this is the definition of bond distance or bond length. Students, now let us move on to bond energy. Bond energy or bond dissociation energy is the energy needed to break a covalent bond between two atoms of a diatomic covalent compound in its gaseous state. Students, the unit for bond energy is kilojoules per mole. A large bond dissociation energy indicates a strong covalent bond. Students, now let us see the limitations or drawbacks of electronic theory of valence proposed by Jean Louis and Kozel. The first limitation is electronic theory of valence stated that bond lengths and bond energies of atoms of different molecules is always same. But later, when scientists practically observed this, it was proved wrong. Students, now let us see bond length and bond energy of some molecules. Hydrogen molecule, bond length is 0.74 angstroms. Bond energy is 436 kilojoules per mole. Fluorine molecule, bond length is 1.44 angstroms. Bond energy is 159 kilojoules per mole. Chlorine molecule, bond length is 1.95 angstroms. Bond energy is 243 kilojoules per mole. Bromine molecule, bond length is 2.28 angstroms. Bond energy is 193 kilojoules per mole. Students, now let us see the second limitation of electronic theory of valence. This theory could not explain the reason for specific bond angles in molecules. For example, beryllium chloride, it has 180 degrees bond angle. Boron trifluoride, it has a bond angle of 120 degrees. Why this specific bond angle is there in molecules? This reason the electronic theory of valence could not explain. Students, even though some limitations are there in electronic theory of valence proposed by Gilbert, Louis and Kozel, this is an important theory in the study of chemical bonding of some ionic and covalent compounds. Students, now let us move on to the second theory, valence shell electron pair repulsion theory. This theory was proposed by Sidgwick and Powell, and it was modified by Gillespie and Naum. So, students, this second theory, valence shell electron pair repulsion theory, is further advancement of the first theory, electronic theory of valence. Here you can see the great scientists, Sidgwick and Powell, and Gillespie and Naum, who were responsible for VSEPR theory, the second theory of chemical bonding. Friends, now let us see the salient features of VSEPR theory. The shape of the molecule is determined by the repulsions between all of the electrons present in the valence shell. Electron pairs in the valence shell of the central atom repel each other and align themselves to minimize this repulsion. Lone pair electrons takes up more space around the central atom than a bond pair. Lone pair attracted to one nucleus, but bond pair is attracted by two nuclei. Students, according to VSCPR theory, if we know the total number of electron pairs in the valence shell as covalent bonds and lone pairs in the central atom, it will help us to predict the arrangement of those pairs around the nucleus of the central atom, and from that the shape of the molecule. Students, lone pair means unshared electron pair or non-bonding electron pair. Presence of lone pair on the central atom causes slight distortion of the bond angles from the ideal shape. The magnitude of repulsions between bond pairs of electrons depends on the electronegativity difference between the central atom and the other atoms. Students, these are the salient features of VSCPR theory, and we will practically see bond angles and shapes of some molecules. Students, the shape of water molecule is bent shape or V shape. The bond angle is 104 degrees 31 minutes. Here you can see the shape of water molecule. Dihydrogen monoxide, IUPAC name of water. Students, the second example is ammonia. The shape is trigonal pyramidal and the bond angle is 107 degrees 48 minutes. Students, the third example is methane. The shape of the molecule is tetrahedral. The bond angle is 109 degrees 28 minutes. The fourth example is beryllium chloride. The shape of the molecule is linear and the bond angle is 180 degrees. Students, let us see the fifth example, boron trifluoride. The shape of the molecule is trigonal planar and the bond angle is 120 degrees. Students, you have to remember the shapes and bond angles of all these 5 molecules: water, ammonia, methane, beryllium chloride and boron trifluoride. Students, the limitations of VSCPR theory are it could not explain bond strengths, and the second limitation is it could not explain atomic orbitals overlap.